Thank you, and thank you for the introduction. So we are from Fimmic, and we give you a practical example of an application from a medical field using deep learning, artificial intelligence in this field. And so I'm the CEO of the company, and I have here also our CTO Tuomas Ropponen with me. So we'll divide this talk so that I'll first describe you some general details about the market and why we are in this field, and some details about our product, and then Tuomas can give you more details about the technical background and run a demo if you're interested in seeing the software in more detail. So we are actually a company spinning off from the University of Helsinki, from the Institute for Molecular Medicine. We were founded in 2013 and started our active operations in 2014. First with the first generation version of the software, and then just recently, last month, we launched the next generation version with the deep learning analytics on top of it. But I'll tell you a bit more in a few seconds. So if we start by looking at the pathology market and the challenges today, cancer gives us a good example. That's the most common disease studied in pathology laboratories today. And due to aging population, there's more and more new patients each year, and this is constantly increasing the number of samples to be studied. However, the number of pathologists is not following this trend. And in fact, many countries and areas suffer from the lack of pathologists. For example, in China, there's 20,000 pathologists when the number should be 100,000 to be on an adequate level for this population. And the microscopy as a technology plays an important role in cancer diagnostics and in all pathology, anatomical pathology diagnostics. And it's been the same for 100 years. It's a subjective manual analysis of the microscope slides. Tuomas has some examples here. How does a slide look like if you don't remember from school? But anyhow, the method itself causes, of course, some risk for misdiagnosis. It's due to the subjectivity of the method. And in some studies, it's been shown that the agreement can be even as low as 48% between pathologists for a specific breast cancer case. So it's certainly not the benefit for the patient, this variance. So there's both the need to improve the efficiency of the analysis and the consistency of the analysis as well. And the first thing to improve the situation is to digitalize the samples, and this is an increasing trend in this industry today. Digital samples are of course easier to archive and to retrieve from the archives to send to remote consultation. But the most significant improvement and the one driving this market forward is the ability to use machine vision and artificial intelligence today to help the experts in the analysis. And this is what we're doing. But there are some challenges as well. And the first one is that these images of microscopy samples, these are huge files, gigapixel-sized files. And then the instruments doing the digitalization, these so-called scanners, they all have their own locked image file formats. So they're not very easy to share with the collaboration networks or even within the lab if they have two different vendors in the lab. And there's been some image analysis tools in this market for these kind of images, but the commercial ones are really, really expensive on-premise installations of the software, and they're all based on so-called conventional first-generation machine vision methods. And they have been in many ways limited and not able to support pathologists very well in the work. So we've developed our product to address these challenges. So we're providing fast and easy access to these modern analysis tools on a cloud platform. And this is how the workflow goes. So our customers, they who do have the samples on slides, they do the scanning. And after that, the images are uploaded to our cloud service. There's a so-called web microscope connector installed on site, which automatically takes an image, compresses it, converts it to our format and uploads it to the cloud. And once there, the images can be viewed with an internet connection with any browser, anywhere our customers may be, and now also analyzed. And we sell this software as a service, so it's a very typical SaaS model. So you purchase an annual fee, the ability to use the software, and then based on the images you store, the how much you analyze, the more you pay then for the software. And it also enables anyone to use this GPU capacity, for example, on a cloud platform. So customers don't need to purchase these servers on site at all. And yes, so we're using these deep artificial neural networks here to teach how do certain targets look like in a tissue sample. I'm going to show you here a few examples. But before that, so we're actually developing a specific neural networks for each specific target separately. And these can be, for example, laborious quantification tasks of certain cells or certain stainings in a sample. We can also segment the tissue based on morphology, and this is something completely novel to this market. We can also detect certain rare targets from these enormous images. Sometimes you only have few infected cells, for example, in a huge blood smear where you need to identify rare targets, and this is something where we can help. We can show you examples later. But this is one of the examples I have here, and it's a breast cancer diagnostic case, and it's about quantifying a Ki-67 biomarker, and this is quantified inside the epithelium part of the tissue. So first we need to detect the epithelium, and then do the quantification of the positive and negative cells inside there. So here we started with selecting, for example, a good image set for the training part. And here, of course, it's important to verify that the training set of images represents very well the actual samples being analyzed later on. And once the training set is selected, then we start annotating them. And actually, in this application, we have a benefit of having a lot of image data in one single sample already. These are huge files, so we cannot annotate them completely. So we start taking these sort of snapshots from these huge files and then annotate them very carefully. And this is an iterative process, the training. So we do first something, then we see how well does it work, and see where it didn't work, and then we take more snapshots for the training and retrain the network again and again until we reach the desired level of sensitivity and specificity. So here on the left-hand side, you can see first the epithelium and stroma segmentation, and then in the right-hand side, the biomarker quantification inside the epithelium. And on our software, so we show and display the results as images on top of the original image. And it's a so-called a pyramid structure where you can really zoom into the cellular level to see the results and the details. So the pathologist or the researcher, they can visually verify the results that the computer gives them. And this is very important. And there's been many research studies where it has been shown that the combination of pathologist and deep learning AI is actually improving even the results given by the machine by 85%. So we're really not replacing doctors here. We are supporting them and giving them sort of a artificial second opinion on their shoulder to verify and give them more support to the diagnosis. Here's a closer look to the cellular level of the results. But basically, this sort of context-intelligent image analysis enables full automation of these tasks, image analysis tasks in this field. And this is something unique. There's no other solution on the market as of today doing this. And if you compare to visual manual analysis, it's of course sure that the machine does always the same way. The quantification, it's tireless. This is another example. It's actually not a cancer case, but this is from a liver biopsy. And here the task is to quantify the percentage of fat in these images. And fat is these white small droplets, which we needed to quantify for this study. And first we started by detecting the area of the tissue. And then we trained the network, how does the fat droplet look like? And of course, this is a little bit awful pictures I can see from here, but in the inside of the tissue there are these white holes, and these are blood vessels, so we needed to teach the network not to count these areas to the tissue area at all. So this was actually quite tricky one, but we managed to do this, so we can give numerical values for the researchers about the quantification and in the consistent way. So you can imagine, so if in this study, for example, they have 300 samples, so you need to be pretty consistent in the visual analysis if you want to do this manually. So we're at this point, we have about 20 different applications on either ongoing or done already, and these are some of the list of examples here. Most of them are related to cancer, but we also have samples from the gastrointestinal tract, as you saw, from the studying Alzheimer's and Parkinson's disease, from the rat brain samples. It's a huge task, actually, in the bottom image here. It's a really awful looking network and mesh where the researchers need to quantify the number of nerve cell bodies in these samples, and it's a pain for them to do manual, and we've automated this for them. But basically there's enormous possibilities for different algorithms to be created in this space. As a company, as mentioned, we were founded in 2013. We've started with the first generation software then, and we've sold it to research customers, to medical education in Europe, North America and Middle East by now. And we just launched the next generation version of the software, and this year we will be bringing more algorithms, more tools. We will be improving our own workflow in algorithm development and aiming to launch to the clinical sector next year. So the first target for us is the research and the pharmaceutical drug development area. So we are actually a great mix of different types of expertise in the team. So we have medical doctors, we have software developers, we have machine vision experts, and long-term life science entrepreneurs, commercial expertise. And this is our core team that you see on the slide. But in addition to this, we have 8 people working in the software development and algorithm development today. And if anyone is interested, we are also hiring at the moment. So let us know if you're interested in joining our machine vision team. And at the end of my part, so the future of pathology, it's really digital, that's for sure. We can see a lot of benefits in using artificial intelligence in this field and how it will completely change it. We are now in a status where we can support decision making by providing more data and quantitative data from the samples to support the pathologists. But very soon, I'm sure that we will be able to give prognosis based on tumor morphology. And after that, it will be possible to suggest even a treatment based on how the tissue looks like under microscope or on the screen actually today. And if you compare this morphological data to the similar patients who have similar symptoms, similar genomic profiles, similar morphological data, you will be able to develop better algorithms for the doctors to help their work. And this is, of course, all benefit for the patient as we can provide more faster and more accurate cure for them. So that's the end of basically my part, so I will give the floor to Tuomas now.